the credit needs to go to the authors of all of those tools for doing the hard work for getting these methods ready. But we are actively contributing back to all of the open source tools that we use. We're improving the methods, we're providing bug fixes. And the main thing that we're doing on top of that is we're making the tools easy to use. So all of these tools are very powerful, but actually getting them up and running and all sitting in the same Python environment and not fighting each other over dependencies and available on different platforms, and sort of available in a way that it can be used to set up a calculation in 10 minutes rather than 10 hours or 10 days. That's been quite a lot of work. So our FEP workflow is pretty standard, really. We're starting off with a set of compounds and a protein. So we're going to generate a perturbation network to look at which compounds we want to perturb into which others. And we then generate the force field parameters, equilibrate each system, generate the input files to SOMD, which is the biosynth-based tool that's actually going to do the heavy lifting of running the Lambda windows. And it's using OpenMM under the hood as the molecular dynamics engine. And then at the end of the day, when all of the Lambda windows are complete, we'll then analyze the resulting network, compute delta Gs for all of the links, and then condense all of that down to a final activity prediction for each compound in the network. So, we're obviously trying to automate this and to make it as easy as possible for our customers to use. There is a sort of level of irreproducible complexity in free energy calculations. They're not really point and click, they are still expert tools. And basically a lot of that is just down to preparation of the system. If you don't understand your protein really well, if you don't have it really carefully prepared, if you haven't thought about solvation networks, if you haven't thought about the applicability domain of your force field and whether it's actually going to be applicable to the interactions that are present in your complexes, and you haven't thought about all of the other things that are involved in really setting up a detailed understanding of a protein ligand complex, then your free energy method's not going to work. And I think we saw in Francesca's talk just how complicated and long an undertaking that can be. So free energy methods are going to remain an expert tool. It's not going to be something that you can bring in a first-year undergrad student to get them to generate brilliant FEP results on a data set with the protein being hauled out of the PDB and point and click quite yet. But what we aim to do is to automate the boring stuff. Okay, all of this stuff, protein prep and so on, does take an expert knowledge and an expert eye. But what we want is to get to the situation where people can spend time thinking about that, but they don't have to spend time writing analysis scripts and moving input and output files between machines and nursemaiding Python environments and things like that, that they can spend their time thinking about the science rather than about the software. So within our software, we've got to the stage where having done all of the complicated stuff of setting up the system and getting a protein prepared and getting your ligands in the right place, actually running an FEP calculation is really simple. You just pick the ligands, you pick the protein, you say I want a new project, and bingo, it creates a new project for you and automatically builds a suggested perturbation network. This is all automated, but obviously automated methods can go wrong. So we will build the best network that we can. And the hard part of building a perturbation network is working out which ligands should be mapped to which other ligands and how difficult those transformations are. We've got a reasonably complicated algorithm to do that in an automated fashion. And that will build the best network it can, but it will also flag up transformations that it thinks are going to be difficult. It's one of the research projects we've got going at the moment is a way to automatically suggest intermediates. So if there's two ligands in the network that really we'd like to be able to join in order to make the network more robust or in order to connect it if it's disconnected, but actually they're just that bit too far apart for us to really be confident we're going to get you accurate delta G values, we should be able to automatically suggest an intermediate structure that you can use to bridge from compound A to compound B. And obviously, the expert here needs to be able to change things, so we make it easy for the user to add and remove links and modify and edit the network. And this can be done both at the start of the calculation, but it can also be done halfway through the calculation, or indeed at the end. If the results just aren't good enough, you can add an extra link or two, delete a link that wasn't working very well, rerun the new calculations, and get an update on your project without having to rerun everything from scratch. So one of the things we've added to the setup system is a distinction between benchmarking and production. So in a benchmark mode, you're going to run it with a bunch of ligands that you know the activity of, but the software shouldn't know the activity of. So in benchmark mode, in essence, the software is going to assume it doesn't know anything about any of the compounds. We'll just set up the best network it can based on the structural and 3D similarities between them. And we'll then generate, in essence, a blind prediction that you can then compare with experimental data to see if your method's actually providing you with any information or it's just being a really expensive noise generator. In production mode, however, you're likely to have a list, a mixture of compounds that you haven't made yet and you would like to predict the activity of, and compounds that you have made and you do want the activity of. And so if you set up the network in production mode, it will use the fact that you've got a whole bunch of molecules here, some are known, some are unknown, to set up an optimal network such that the distance from the unknowns to the nearest known is minimized. So we don't want a compound that's unknown to have to hop through 3 or 4 links before you get to a known compound, because that's going to increase the noise available, the noise in that prediction. So we'll try and generate the network such that each unknown has the shortest possible path to the knowns. We can use the links between the knowns as part of this sort of hysteresis and cycle closure error analyses. But again, the software knows that in this case, compound 20A and compound 20C are both known. We can use this link in our error analysis, but we don't need to compute it. So we're not going to actually use any computing resources on that if we don't need to. So obviously one of the other things that you may need to change is the atom mapping. And again, our atom mapping is usually pretty robust, but there's always edge cases where either due to sort of pseudo-symmetry in your ligand or to other reasons that the default mapping we might produce can go wrong. And in this case, it's because there's often a tension between the topological atom map, so which atoms just match the atoms on other molecules based on pure sort of graph similarity, and 3D placement, because we assume that you spent a little bit of time making sure all of your ligands are placed in the active site in what you hope is more or less the binding conformation. And usually these two agree, sometimes they don't. And in that case, we'll make a decent stab as to what's the best mapping. But it's something that we found that you need to go and manually override on the rare occasions when the automated mapping doesn't give you what you think is the right answer. And then having done all of that, from that point onwards, the whole thing is completely automated. You set up the system to know about your computing cluster, either internally or on the cloud, and hit go, and it will automatically, if it's running on Amazon, for example, spin up a cluster, run your calculations, and then shut down the machines as soon as the calculation's going, so that you don't provide Jeff Bezos with any more money than is absolutely necessary, because he's already got enough, to be perfectly honest. And obviously, once the calculation's finished, we want to provide you with a way of visually analyzing the results as well as possible. So we do all of the usual things. You can view the overlap matrix and cycle errors. You can visualize some of the trajectory data and just make sure that the system has behaved itself. If it's a benchmark calculation, you can look at the activity plot and see all of the results there and how well you're actually doing in terms of predicted versus actual activity values. So one of the things that we've sort of added in that we find to be quite useful is something that came from a paper that was published a short while ago on methods of evaluating free energy calculations, and that's the overlap matrix, which is a measure of how well each lambda window is overlapping the lambda windows to either side of it in terms of phase space. So if your lambda windows are too far apart, you'll end up with poor values in your overlap matrix, and that indicates you're likely to have convergence problems. Conversely, if your lambda windows are all good, that makes it less likely that you're going to have convergence problems. You're not absolutely guaranteed, but at least less likely. And so having run a calculation, we'll flag up links that we think have a potentially poor overlap matrix for you to go and investigate. And if it does look like it's poor, rerun with a higher number of lambda windows. One of the research projects we've got underway at the moment is a method of extending this to automatically determine an optimal lambda schedule for each transformation, so that rather than using either a linear lambda schedule or a non-linear but sort of fixed lambda schedule for each link, we'll be using lambda values which are non-evenly spaced between 0 and 1 in order to maximize the information content in the minimum amount of compute time. So how well do we do? Obviously, what everybody does the moment they've got a free energy method is you go and test against the original sort of benchmarking data set that Schrödinger published a few years ago, the sort of Wang et al. Data set. And running on that, we performed pretty well. Results both in terms of R squared and in terms of mean unsigned error, comparable or possibly very slightly worse than FEP plus. It's sort of within the statistical noise there. On average, we are slightly better than both Amber TI and the non-equilibrium method that was published by Gapses et al. Towards the end of last year. So, on the whole, we seem to be doing okay. Obviously, there's room to improve. We'd like to get better, but so would everybody else. And if you're interested in the details of the benchmarks, we published a paper towards the end of last year, which goes into overly exhaustive detail as to how the method works and how we ran the benchmarks. And it includes all of the actual data sort of underlying all of those graphs. So if other people want to compare themselves to us, all of the per link values are present there in the supporting information. So you can go and dig behind the headline numbers. So one of the things that we've been doing more recently is looking at ways of improving the speed of the calculation, because obviously throughput is quite important in free energy calculations. These aren't cheap, and if you can push more compounds through, that does improve the value of the technique. So by default, for sort of your maximum information content, because we're running a single topology mode, turning A into B isn't the same calculation as turning B into A, quite apart from anything else, because the A into B calculation, we start with a system that was equilibrated against compound A. For the B to A calculation, we start with a complex that's equilibrated against compound B. Now, in an ideal world, if everything's converged, these should be the same. In a non-ideal world, which is the one we live in, these are rarely exactly the same. But running each link in both directions does give you a good error statistic, in that it gives you a hysteresis for each link, which is very useful as a measure of how much you should trust any individual pairwise transformation. So these are very useful for error detection. If you're really interested in getting accurate results, doing each link sort of twice once in each direction is a great idea. However, that obviously halves your throughput. So if you want to go more quickly, you want to be running in a fast mode where you do each link only once. But then there's a question of which direction. And we didn't want to do it just on a completely random basis, that whichever ligand his name is alphabetically first is ligand A, and it moves to the other one. So there's then a distinction for a question rather for how do you choose which direction you're going to go for any given pair of links. And the obvious criterion here is size, that you can either start with a smaller ligand and grow it into a bigger one, or you could start with the bigger ligand and shrink it to the smaller one. Obviously, there are going to be cases where actually the transformation involves removing a group from one side of a molecule and moving it to another where there's no net change. And for those, we will end up having to be more or less arbitrary about which direction we do. But size seemed to be the obvious criterion to use as an automated method of running each link only once rather than twice. So we've done a fair bit of sort of experimentation here. So these are the results if we look at the Wang data sets. And look at how we do with all of the links being done in both directions versus all of the links being done either small to large or large to small. And so the good news is most of the time, actually, it doesn't matter that much. Most of the time, both the R squared and the mean unsigned error numbers really aren't that different, running just in one direction rather than in both directions. So that's good. It means if you run in fast mode, you're probably getting results that are of a comparable accuracy to if you ran in both directions. But obviously what you lose out on is a little bit of a warm fuzzy feeling about how accurate each link is. And you've got a better idea of if there are errors in your simulation, where they're likely to lie and which ligands they're likely to affect. So based on these results and some other experiments we ran, overall it looks like the winner is small to large. In general, you want to be growing the smaller ligand to create the larger one. And that sort of is in accord with suggestions that have been made in the literature over the last couple of years as to which is the correct direction to run these things in. So the other thing I want to present is another benchmark data set. So this is the one that was published by a group from Merck, Schindler et al. We were able to run this and a bunch of other sort of internal benchmarks because we obtained a grant from the HPC Europa 3 project, which gave us a considerable amount of time on European supercomputers, which is very nice. The only thing that wasn't nice is the supercomputer we got time on was brand new and just being commissioned. And so this has taken a lot longer than we thought it would, simply because of teething troubles in getting the cluster up and running. So as a result, we've had less time to analyze this data than I would like. The last results only came in towards the end of last week, so do bear with me. This data set proved to be difficult for us to analyze simply because at the moment, this is something we're working on, but at the moment we don't have the capability to do net charge changes. And a large proportion of the data sets from the Merck paper, there's 8 data sets, I think 4 of them have got a mixture of both positive and neutral compounds in them. And so as a result, we can't do those data sets all in one. We have to split them into subsets and analyze the neutral compounds and analyze the positive compounds as separate data sets. And that makes it rather difficult to compare our results in this benchmark against the published results from FEP Plus that Schindler provided. So, a direct apples to apples comparison isn't really possible, but we're going to do the best we can. So the numbers we can compare is we can compute pairwise RMSE values. So this is looking at each pair of ligands that we computed a link for. What was the error between the delta delta G that we predicted and the experimentally measured delta delta G? What's the RMS value of those errors? It's not a complete apples to apples comparison because we use a different network to FEP Plus, so the actual links are different. And this comparison, I'm going to be completely straight, does actually favor us slightly because, of course, we don't have any links that are going from neutral to positive compounds or vice versa, and those are known to be slightly more tricky. And so we're including the RMS only over potentially the slightly easier links in the data set and leaving out some of the more difficult ones. So I just want to be honest with that up front. So if we have a look at the data for pairwise RMSE, again, we're roughly comparable to the results that were published for FEP Plus. There's a couple of data sets that we do better on, CDK8, and KS2. There's a few, so these two and these two that we do somewhat worse on, and there's a couple where we're basically the same within experimental error. So that's sort of consistent with the results that we saw from our earlier study on the Wang data set. The other numbers that we can compare, as well as the pairwise RMS error, is the Kendall-Tor, which is one of the statistics that actually people are really interested in. That's how well are you actually ranking compounds in terms of saying compound A is more accurate than compound B. Again, the difficulty here is we can't get a Kendall-Tor over the entirety of each data set because we can rank all of the positive compounds in a data set and we can rank all the neutral ones, but we can't rank the positive ones against the neutral ones. So in this case, what we're going to present here is just the Kendall-Tor values for the larger subset. So if a data set has more neutral compounds than positive ones, we'll just do the Kendall-Tor for the neutrals. If there's more positives than neutrals, then we'll do it just for the positives. To be honest, doing it this way probably slightly disfavors us because a number of the data sets have the property that all of the highly active compounds are positively charged and all of the weakly active compounds are neutral. And so if you just take one of those two subsets, you end up with a very small dynamic range. The range of experimental activities is quite low, and that makes it very hard to get a good rank ordering because the experimental rank ordering is much less certain because the compounds are very close in activity. So on that basis, again, there are a couple of data sets where we do better than the results from FEP Plus. There are a few where we do slightly worse. And there are a couple that we just completely bomb on. One of these is due to poor dynamic range. The other one we just don't do very well on. And at the moment, I don't know why, but we only got the results for that back last week. So it's one of the things we're going to be looking at. It's possible we made an error in that calculation. We just haven't noticed it yet. I haven't had time to work it up fully.
Mark, can you please start wrapping up your presentation? Thanks.
I've got 2 more slides. Okay, so the last thing I'm going to share is in terms of ligand force fields. So for the protein force field, we're using AMBER, FF14SB. For the ligand, we're using either GAF or OpenFF. We're members of the Open Force Field Consortium. And so we've run some analyses looking at the Wang data set, both in GAF as a ligand force field and in OpenFF. And the results here are basically that the two are statistically indistinguishable. There's really no difference between the two. We did this comparison a while ago using OFF 1.0, and at that time, OFF was worse than GAF. So OFF is now at the stage where it's comparable to GAF and possibly very slightly better, although not statistically significantly. And given the state of progress of the Open Force Field Initiative. It's been less than a year to go from noticeably worse to about the same. I can predict that by this time next year, the Open Force Field will be noticeably better than GAF, and at that point we'll switch to it being our recommended force field to use in these calculations. So that's all I have. Thank you very much for listening, and I'm happy to answer any questions that people may have asked.
Thanks, Mark, for the great presentation. We're running a little bit short of time here. You have 3 questions on the Q&A. I'll just say one so you can quickly answer it, and we can move on. This comes from Lee Young Park. Thanks for sharing your impressive progresses. A quickie. Does RMSE refer to systematic error, say deviation, to experimental numbers?
Yeah, so the pairwise RMSE numbers are, if you take each pair of compounds that we computed a delta G for, we know the experimental delta G between those and the measured activity values. We've got a computed delta G, and we just take the difference between those as being the error number, and then we just compute the root mean square value of those errors. Those are the same numbers that were published in the Schindler paper.
Great, thank you very much. Our last speaker of the session is Isegul Ozen. I'm pretty sure I